We all grew up thinking matter came in just a few flavors. Solid, liquid, gas, maybe plasma if your science teacher was cool. But now, scientists have created a substance that mimics the early universe, one that breaks time, and another that just might be from another dimension. I'm Mike with List 25, and these are 25 times scientists created astonishing new states of matter. Alright, let's get our inner geek on. You wouldn't be here if you didn't secretly want to. I'm going to try to break everything down on today's list to the bare bones. In 2017, a group of researchers at the University of Maryland lined up a bunch of ions, ytterbium if you're curious, in a fancy laser trap and then kept zapping them at regular intervals. Usually this would lead to a nice predictable pattern, atoms doing what they're told, syncing up with the laser's rhythm. But not this time. Instead of falling in line, the particles settled into a rhythm of their own, flipping every other beat, like a dancer ignoring the music, but somehow still perfectly on time. It doesn't sit still, it doesn't flow. It ticks in a quantum rhythm. They call it a discrete time crystal, a phase of matter that doesn't just exist in space, it lives in time. Then again, our next phase of matter couldn't decide if it wanted to be solid or liquid, so it just chose both. In 2019, researchers in Stuttgart created the world's first supersolid. They chilled a bunch of magnetic atoms, dysprosium if you're into rare elements, down to near absolute zero and got them to lock into a crystal-like structure. So far, so solid. But then they realized the same structure could flow. Picture ice that glides like a superfluid without ever melting. It sounds impossible, but they confirmed it by detecting two separate sound waves moving through the system. One tied to the solid structure, the other to the fluid motion. They literally created matter doing two opposite things at once. That same dedication showed up again in 2025 when scientists at Washington University in St. Louis managed to build a system that runs on overlapping clocks. But before I can tell you about that, let me quickly explain what a time crystal is. A normal crystal, like a diamond or a snowflake, repeats its pattern in space. Zoom in, and the structure looks the same again and again and again. A time crystal is similar, but in time. Its internal pattern repeats when you push it, like hitting a button and having it respond on a loop, even though you're not giving it enough energy to do that. Now, during their experiments, the team at WU blasted diamonds, specifically with ones with a special kind of defect inside, with microwave pulses, basically waves of energy. And instead of responding with one clean rhythm, like tick-tock, the system started pulsing in several rhythms at once. In essence, it created a new structure in time, not space, that was patterned, but not perfectly regular. They're calling it a discrete time quasicrystal, and with any luck, it might help them make sense of the more complicated corners of quantum physics. Now imagine a liquid so small and strange that it holds itself together without any kind of form or container, and flows without any resistance. Yep, its creators decided to call it a quantum droplet. In 2024, physicists in Innsbruck brought the temperature of a bunch of atoms down to almost absolute zero, like colder than space, and prodded them with a magnetic field. Instead of acting like a gas or freezing into a solid, the atoms clumped into a tiny blob that just floated there. It was dense like a solid, but it also moved like a perfect liquid. It's somewhere between a tiny drop of fog and a raindrop, and scientists everywhere are now trying to figure out what else this strange little droplet can do. Over at Harvard and MIT, a group of researchers pulled off something strange. They ended up with a kind of liquid that isn't a liquid at all. Back in 2021, they arranged rubidium atoms into a triangle grid and cooled them down, almost to absolute zero. Normally when things get that cold, the atoms' magnetic spin fall into line, all pointing the same way like tiny little compass needles. But these didn't behave. The spins kept jumping around, non-stop, in no real pattern, like they couldn't make up their minds. What they'd found is now called a quantum spin liquid. It's not a liquid in the regular sense. The name comes from the way the magnetic stuff flows and shifts around. And if it lives up to the hype, it could be a game changer for quantum computers, especially the kind that mess with particles that can be 1 and 0 at the same time. Oh, this? Yeah, you've probably seen me messing with it before. If you've been here before, you know I love fumes flavors. Like, probably too much. I go through phases. Orange vanilla had and has me in a chokehold. Then it was spearmint ice. Cinnamon hearts made a comeback about 2 weeks ago. I even gave black licorice a shot. Don't judge me. But now, they have gone and dropped mango. And I absolutely love it. It's bright, juicy, tropical, almost like a vacation in core form. It is perfect for pretending that you're not just stuck at your desk while everyone else is out there getting their summers on. Like, yeah. Oh, it's great. If you're new here, let me assure you, no, I don't have any terrible habits. This isn't a vape. It's flavored air. It doesn't have any vapor, nicotine, or batteries. It's just a well-built little device that gives your hands something to do that isn't opening snacks. You can twist it, you can play with it. It's got a little magnet. See? And, well, do I need two? No, but mango is doing things to me, and now I'm switching them out like moods. If you've already got a fume, you'll want to try this one. And if you haven't jumped in yet, this is your sign. Right now, if you grab the Journey Pack using my code LIST, they'll throw in a free fume topper too. It's on this one, but it's black on black, so it's hard to see. Just head to tryfume.com/list or scan the QR code on screen. All right, back to it. And yes, I'll probably be holding this in the next segment too. So let's not act surprised. All right, now let's take that same weird particle behavior and see what happens when you mess with electricity in ultra-thin layers of carbon. A few years back, Columbia University's best and brightest stacked 2 sheets of graphene, that's just carbon stripped down to a single atom, with a wafer-thin insulator in between. They set it up so one layer carried electrons, while the other handled the little gaps the electrons left behind. Then they cranked up the magnetic field and chilled the whole thing down to near freezing. And that's when it got interesting. The electrons and holes started pairing up across the layers, almost like they were dancing. Suddenly, the electrical resistance nearly vanished. They'd created what's called an Exciton condensate, sort of like a superfluid, but made from pairs of opposites. And it might be a stepping stone to ultra-efficient, low-power electronics. However, not every exciton wants to flow. In 2023, scientists found a way to trap them, and also created an exotic new state known as Bosonic correlated insulator that doesn't conduct at all. They placed 2 wafer-thin semiconductor layers on top of each other. One made from tungsten diselenide, and the other from tungsten disulfide. And when they cooled and turned them just right, the particles inside didn't move. At all. The excitons lined up into a tidy frozen grid. What makes this so unexpected is that excitons aren't supposed to behave that way. They're lightweight, they move, they flow. But in this state, they were locked in so tightly that scientists could literally see the structure under a microscope, and it didn't look like anything we've seen before. We've also produced something that's ice, but it flows. It's solid, but not really. In 2019, scientists at Lawrence Livermore National Lab blasted a sample of water with powerful laser shocks, the kind that generates millions of times the pressure of Earth's atmosphere and temperatures hotter than the surface of the sun. For a brief moment, they achieved a bizarre new phase called Superionic Ice. In this state, the oxygen atoms lock into a rigid crystal-like structure, like a solid, while the hydrogen ions move freely through it, like a liquid. Scientists believe that it's the kind of ice that exists deep inside planets like Uranus and Neptune, but 2019 was the first time we ever saw it in a lab. Either way, another team turned up the magnetic field and watched matter start radiating together. Researchers working with a crystal called ERFeO3 cooled it down and hit it with a magnetic field almost 200,000 times stronger than Earth's. Under those extreme conditions, something remarkable happened. The tiny magnetic spins inside the crystal, the ones tied to ion and erbium atoms, started oscillating in perfect synchronization. It was a full-on superradiant phase transition, a shift into a state where the material itself emits light collectively. Almost like every atom had suddenly agreed to shine at the same time. Scientists have been trying to observe this for over 50 years, and in 2025, they finally pulled it off, showing it's not just a theory anymore, but a real observable state of matter. Scientists at Rice University took it a step further and built something that looked like one oversized atom with a bunch of others trapped inside. In 2018, they cooled a gas of strontium atoms down to near absolute zero, cold enough to form a Bose-Einstein condensate where everything starts acting like one big unified particle. Then, they excited a few of those atoms into a super high energy state called a Rydberg state, where the atom's outer electron orbits way farther out than usual. That orbit got so large it actually surrounded dozens of nearby atoms, and instead of knocking them away, it kind of held on to them. The result was a Rydberg Polaron, a huge, hazy atom with a cloud of other atoms loosely bound inside it. It's weird and fragile, but it gave scientists a whole new way to explore how particles interact over long distances in a quantum system. Figuring out how particles move, and how to keep them from scattering, also led to a major breakthrough with light itself. In 2024, scientists at Rensselaer Polytechnic Institute engineered a photonic topological insulator. In short, they built a material where light can travel around the edges without getting blocked, bounced, or thrown off course. It works like a protective highway for photons. The center of the material blocks the light completely, but the edges let it cruise through effortlessly. This kind of light-based control could eventually help us to build quantum circuits that don't break when you sneeze on them. And it's one of the first real-world steps towards using light the same way that we've learned to guide electrons in specially designed materials. Back on the molecular side of things, scientists were figuring out how to get entire molecules to collapse into one coordinated quantum state. A team at Columbia University dedicated 2024 to cooling down a bunch of sodium-cesium molecules to just a few billionths of a degree above absolute zero. At that point, the molecules stopped acting like individual particles and started behaving like one single giant one. It's called a Bose-Einstein condensate, and this was the first time anyone had made one out of molecules instead of atoms. Even better, it lasted 2 whole seconds, which is actually a big deal in a world where most of these things disappear in a matter of milliseconds. Okay, are you still with me? Would you believe me if I told you that we've also recreated the stuff that existed right after the Big Bang? When we hit the new millennium, scientists at CERN smashed heavy lead ions together at nearly the speed of light, and for the tiniest fraction of a second, they broke matter down to its raw ingredients, quarks and gluons. Normally those particles are locked inside protons and neutrons, but in this state, lovingly named quark-gluon plasma, they're set free, swimming in a hot, like 4 trillion degrees Celsius, dense soup, not the kind you eat obviously, that's thought to have filled the universe just microseconds after it began. It didn't last long, but for a brief moment we had the early universe in a bottle, and that changed everything we thought we knew about how matter works. Which makes it even stranger that just a few years later, physicists managed to trap matter in place without even freezing it. They built a kind of atomic maze out of overlapping laser beams, just enough structure to confuse the particles inside. And when they dropped ultra-cold atoms into the setup, the particles didn't spread out or flow like normal, they just stayed put. This unique, glitchy behavior is now known as two-dimensional Bose glass. It acts like a jammed-up quantum system, and it could actually turn out to be great for keeping quantum systems stable and data intact. Of course, locking particles in place isn't the only weird trick matter can pull. In this next case, they turned into an actual puddle of electricity. In 2014, physicists battered a chunk of gallium arsenide with ultra-fast laser pulses, and for just a few trillionths of a second, hundreds of negatively charged electrons and their positively charged counterparts, called holes, glommed together into one loose, fluid-like blob. It wasn't a solid, and didn't spread like gas. It moved in sync, like particles in a droplet. So they named it a Dropleton, a fleeting little liquid made entirely out of charge. It didn't stick around long, but while it lasted, it showed scientists how quantum particles can act as a group, not just as loners or pairs. Not to be outdone by puddles of electricity, scientists recently uncovered a magnetic state that's somehow both hot and cold at the same time in the same place. And it's me, because I'm hot and cool. That was dumb. Anyway, the Brookhaven National Lab team cooled a special magnetic material and applied a powerful magnetic field. Then, things got weird. Like my last joke. Half the electron spins locked in a frozen ordered pattern, like a row of compass needles. The other half kept flipping and dancing around as if nothing had changed. This split personality, officially called a coexisting spin state, behaves like part of the material is made of magnetic ice and the other part is still on fire, and could help them design new kinds of memory or spin-based electronics with ultra-fast switching power. Like the Switch, too. Does the Switch even have switching power? You've probably noticed that Bose has shown up a lot on today's list. And it's not just because physicists like naming things after Einstein's buddies. Bosons are particles that cooperate. They can all pile into the same quantum state and act like one big system. That makes them ideal for creating weird new phases of matter. In 2023, scientists leaned into that and built a Chiral Bose-Liquid. They created a special semiconductor setup that forced the particles to flow in just one direction along the edges. And when cooled, those bosons didn't just flow, they moved in perfect coordination. Tweak one, and the whole system responded, like a quantum hive mind. It's the kind of collective behavior that could help us design new ways to transfer quantum information, especially in systems where we need everyone on the same page, no matter what. Moving on, we've also learned that you don't even need atoms themselves to be the fluid. Light can take the lead. Now, we've already seen light rerouted through special materials, but this one's different. In 2024, a team at the University of Bonn got photons, literal particles of light, to behave like a gas. They fired lasers through a custom-built optical fiber filled with a glowing dye and trapped the photons just long enough for them to bump around, spread out, and settle in a kind of balance. What they ended up with was a one-dimensional photon gas, basically a quantum liquid made entirely out of light confined to a single line. It's a new way to study quantum behavior using light, and it's proof that even something as massless and speedy as a photon can be persuaded to act like a relaxed, well-behaved fluid. Now I'm thirsty. I need fluids. Which brings me to Exciton condensate. And a quick heads up, this is not a repeat of number 20. It's the same family of particles, but the behavior here is totally different. Both cases involve excitons, those neutral little pairs that form when an electron links up with the positively charged hole it leaves behind. And yes, in both, those excitons settle into the same quantum state and start behaving like one big coordinated fluid. But this time, in 2017, researchers at the University of Illinois cooled down a layer crystal called Tasnices to nearly absolute zero. And instead of flowing like they did in graphene, the excitons locked into place. What they found was a totally new charged neutral phase of matter, an excitonic insulator. And because scientists love naming things before they're real, well, they already had a label ready. Excitonium. After decades of speculation, they finally caught it in action. On the flip side, in 2025, a team at Caltech used lasers, or maybe I should say tweezers made of light, to trap and twist atoms into a new quantum state called multi- or hyper-entanglement. Some call it multi, since not every researcher likes to call it hyper-entanglement. They've got their own politics. Normally, entangled atoms share one connection. Maybe it's a spin, maybe it's momentum. But in this case, the researchers got them to link up across multiple properties at once. These atoms were tangled in every direction. Spin, motion, energy levels, the whole works. Think of it like this. If normal entanglement is helpful, this is like giving it a promotion, a gym membership, and an Italian coffee. It does way more. Anyway, in 2025, researchers at Institut Fresnel identified what might be the most contradictory thing yet. They found a supersolid made of light. They etched microscopic ridges into a chip, hit it with a steady laser, and persuaded the photons inside into lining up like a crystal. Amazingly, that same light also flowed with zero resistance like a superfluid. Just a very flowy glide. There we go. It was the first time anyone had ever seen solid and fluid behavior in light itself. And it's not just good for bragging rights, this could be the blueprint for quantum devices that run entirely on light. And then there's swirlons. We all know that Newton's second law of motion is a cornerstone of physics. Push harder and something moves faster. But that only applies to things that aren't moving on their own. So researchers in England decided to see what would happen if you break that rule at the particle level. They built a computer simulation full of self-propelling particles that had built-in energy, but no control over where they went. What happened next threw everyone. The particles gathered into spinning formations, which the team named swirlons. And these swirlons didn't behave normally. When an external force was applied, they didn't accelerate, not even a bit. So Newton's second law basically went out the window. Although it's only a simulation for now, they named it a Swirlonic State of matter, and it could eventually help us understand how flocks of birds or swarm of insects seem to move as one. So swirlons prove that even Newton wasn't perfect. Non-Abelian topographically ordered states, on the other hand, are making us question whether we ever understood quantum behavior to begin with. I mean, I know I do. I know, it sounds like a word salad, but here's the idea. The scientific minds at Harvard used a special quantum processor to simulate tiny particles called anyons, and then move them around in specific patterns to watch how they reacted. What they found was amazing. The particles didn't just flip like a switch. They changed in a whole new way, depending on how they were moved. That is the non-Abelian part. The outcome depends on the path you take, not just the start and end points. It's the first real step toward a quantum computer you could use without needing 20 backup systems and a physicist on call. At number 2 on our list today is a state of matter that's been playing hard to get since the 30s. And in 2025, we finally got to see it. Now, I know you have heard the word quantum a lot today, but hang in there. This one is called a topological superconductor. And it doesn't just sound cool. It could be the cornerstone of quantum technology that actually works without constant babysitting. A team from Microsoft and UC Santa Barbara built it on a chip nicknamed Majorana 1, designed to host particles that are their own antiparticles. These so-called Majorana 0 modes can store quantum info in a way that's almost immune to outside noise. So there are no resets every 5 seconds and no breakdowns if the lab door creaks open. If we can scale it, well, that's a whole new ballgame. And finally, I bring you the Fibonacci time crystal, a state of matter that makes our first entry look basic. Remember at number 25 where the atoms danced their own rhythm and created a time crystal? Well, in 2022, scientists owned that idea and took it a step further. They used a quantum computer to zap atoms in a pattern based on Fibonacci numbers. You know, that sequence where each number is the sum of the two before it? Instead of ticking in a steady loop, the atoms started following a rhythm that never quite repeats in the same way, but that also isn't really random. And that odd timing turned out to be incredibly useful. It kept their quantum behavior stable for longer than usual. The real win here? We found a way to encode quantum information into something as absurd and abstract as a math pattern, and it actually works. And that's a wrap. But before you vanish into the quantum foam, tell me, which of these is the hottest thing humans have ever created? A, the core of a nuclear explosion. B, the sun's center. C, lightning. Or D, core gluon plasma. Drop your answers in the comments below, and no Googling. Let's see who's actually been paying attention. And if you're still in the mood for surprises, check out our related video, 100 Things You Never Knew About the Earth. From strange natural phenomena in hidden places to jaw-dropping records and discoveries, it is packed with everything that you need to keep your brain busy until our next video drops. And maybe then you can pronounce brain better than I can. Hit subscribe, ring that bell, and I'll see you again next time. Told you I was thirsty. See ya.